Thank you and welcome to Shock Mechanics, the basics of shock mechanics. This is a seminar presented by Lord Corporation. Shock mechanics. In the world of shock, these are incidences that occur as drops or impulses that are impacted on equipment. So the first one that we're going to encounter is a half-sine shock pulse. The magnitude of acceleration pulse is given in G's, which is the y-axis, and the time domain is t sub 0, which is the x-axis. We define the shock pulse for a half sine in these terms of G's and duration t sub o, which is always given in seconds. By taking any shock signature and reducing it to the equivalent change in velocity, we are able to compare different shock signatures. In the formulas there, small g is the gravitation constant, and today it will be 386.2 inches per second. The second type of shock pulse you may encounter is a triangular shock pulse. Triangular shock pulses can also take the form of an initial peak or terminal peak or a sawtooth pulse. This is representative of a ballistic type of incident. Again, the delta V can be calculated by G gravitation constant, the G's in, and T sub O is the time domain, all divided by 2. Drop shock is also associated with the term oops, occurs when an object is dropped. The velocity change for a drop shock is a function of the height of the drop. This equation assumes that the package lands flat, not on a corner, and the impact is completely inelastic. Instances where it's a corner drop require different calculations and are more involved. The last type of shock you may encounter is velocity shock. Velocity shock occurs when an object moving along at v1 instantly stops, or an object moving at a certain velocity v1 accelerates to a high velocity v2. Again, the difference between the two velocities is the delta V that we can use. Fragility level is the highest vibration or shock level that can be withstood by the equipment without failure. These are typically very hard to determine, and there is no website or information that you could go to get these fragility levels. In some instances, you may have to use several different values of fragility level or G's out and determine what dynamic deflection you can achieve in your system. Non-isolated systems. In an unisolated system, there is no shock mitigation between the outside environment and the device. In an unisolated system, the peak acceleration is approximately equal to the peak acceleration of the equipment. Therefore, your input is exactly the same as the output. The area under the curve is the same for the input and output. Isolated system. In an isolated system, there is mitigation between the outside environment and the device. In an isolated system, energy input is dissipated over a longer period of time, so the peak acceleration is lower. We're not changing the area of the curves, but just increasing the time domain and reducing the acceleration levels. Output acceleration. The acceleration level resulting from the occurrence of a shock incident to a spring mass system or a free body is the output, or G's out, that we're looking for. This is calculated by taking your natural frequency times the change in velocity divided by 61.4. Dynamic deflection. The dynamic deflection of the isolator under shock is the result of a transient phenomenon and is therefore a single amplitude quantity. This should not be confused with dynamic displacement resulting from sine vibration, which is given in double amplitude. Dynamic deflection can be calculated by taking the change in velocity divided by 2 times pi times the natural frequency. Limitations of the shock equations apply only when the time domain is small compared to the period of the natural frequency of the system. Otherwise, the system will amplify acceleration, and other more complex equations must be used. So t sub 0, the time domain, should be less than or equal to 1/4 the natural frequency. Sway clearance. In any base-mounted system, we must induce what the sway clearance S is going to be at the point of maximum excursion. Note that the calculated dynamic displacement occurs at the isolator or mount and could be aggravated by the geometry of the package design, as in a base-mounted system. In some instances, the secondary collision of the package to the outside container wall may be worse than what initially caused the package to deflect. Shear mounts. This is a flex bolt sandwich mount installed in shear. The load is perpendicular to the center line of the studs. This allows the rubber section to operate in shear. The result is a very soft system that provides maximum protection in the vertical and fore and aft directions and good protection in the lateral direction. Compression mount. This is a flex bolt sandwich mount installed in compression. The load is in the same direction as the center line of the studs. This system provides greater lateral fore and aft protection with less vertical cushioning. This is the same mount that was shown in the previous slide, just installed in a different direction. Load versus deflection. This is a typical load versus deflection curve. The x-axis is the load in pounds. The y-axis is the deflection in inches. The stiffness or spring rate of a mount is a function of its modulus, geometry, and load direction. As the curve illustrates, the compression stiffness is much higher than the shear stiffness. This relationship is typical of a sandwich mount. The shear stiffness is much softer than the compression spring rate. This is a demonstration of shear and compression mounts. The sandwich mounts shown in the two demos are installed in shear. These are the same mounts, just installed in different orientations as we described in the seminar. This is a shear mount where you could see we have quite a bit of deflection capability in the mount that isolates the package when you have a given shock input. The same isolators can also be installed vertically, which gives it a different deflection characteristics and a different natural frequency. So that's why it's critical and important that you tell us which way your isolators are mounted in your application, because we can have different performance in shear versus compression, especially with sandwich mounts. Now we would like to talk a little bit and go over a half sine shock problem. We were given an input acceleration of 20 G's half sine pulse. The pulse time is 11 milliseconds, which is 0.011 seconds. The fragility level of the item that's exposed to this shock is 15 G's, or 15 G's out. We would like to find the natural frequency that's required and the dynamic deflection at the isolator once it's exposed to the half sine shock. The first thing that we need to do is calculate the equivalent velocity shock for the input pulse. Delta V is equal to 2 times G, gravitation constant, times the Gn, times T sub O, divided by pi. Plugging in our knowns, we have 2 times 386 times 20 times 0.011 seconds, divided by pi. We have a change in velocity of 54 inches per second. We can now use that to determine our natural frequency. G's out is equal to natural frequency times the change in velocity divided by 61.4. Plugging in our knowns, we have G out of 15 equals Fn times 54 divided by 61.4. Solving for Fn, the natural frequency is 17 Hertz. Now we can calculate the dynamic deflection at the isolator. The dynamic deflection at the isolator is equal to delta V divided by 2 times pi times Fn. Solving for d sub d, the dynamic deflection, we get 54 divided by 2 times pi times 17 Hertz. We get a dynamic deflection at the isolator of 0.51 inches. The last problem that we're going to cover is a drop shock problem. We're given a drop height of 36 inches. The item's fragility level, or the amount of G's it can withstand and still operate, is 35 G's, otherwise known as G out. We want to determine our natural frequency and the dynamic deflection. Again, we have to calculate the equivalent velocity shock for the drop. A drop shock is equal to the delta V is equal to square root of 2GH. Plugging in our knowns, we have the square root of 2 times 386 times the 36 inches. We have a change in velocity of 166.7 inches per second. We can use this information now to calculate the desired natural frequency. G out is equal to delta V times Fn divided by 61.4. Solving for Fn, we get Fn is equal to 61.4 times G out divided by the change in velocity. That's equal to 61.4 times 35 divided by 166.7. That gives us a natural frequency of 12.9 Hertz. Now we can use this information to calculate the dynamic deflection at the isolator due to a 36-inch drop. The dynamic deflection is equal to delta V times 2 times pi times Fn. Plugging in our knowns, 166.7 divided by 2 times pi times 12.9, we get a dynamic deflection at the isolator of 2.06 inches single amplitude. That is the amount of deflection that the isolator has to deflect on the initial drop of 36 inches. Thank you.